Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome back to the deep dive. If you're learning to fly, your cockpit scan is just everything.
It really is.
You're trying to juggle pitch, power, performance, and a big part of that often is staring at this tiny needle telling you if you're going up, down, and how fast.
That's the vertical speed indicator, the VSI, or sometimes called the VVI. And yeah, it's absolutely essential, especially when you're starting out trying to get those climbs and descents stable or, flying on instruments.
Right. But the way it works, the actual physics, it's kind of neat and maybe not what you'd first expect.
It's often misunderstood, that's for sure.
So our mission today is to get past just, reading it up for climb, down for descent. We want to really understand the clever engineering behind it. How does it actually do that?
Exactly. We're going to dig into how it uses pressure differences to give you that reading in feet per minute, FPM.
And knowing that helps you deal with its quirks, let's say.
Definitely. Because it has inherent limitations. I mean, when it's working right, it has to show 0 in level flight. That's a requirement. Okay.
But yeah, understanding how it gets to 0 or how it shows a climb, that's key.
All right, let's get into the mechanics then, because this is the slightly weird part. It runs entirely off static pressure, right? Just the static port connection.
Correct. Only static pressure.
But it's not like the altimeter, which just reads the absolute pressure. You said it's a differential pressure instrument. That seems contradictory.
It does seem that way at first.
Yeah.
But the VSI cleverly uses that static pressure against itself.
Yeah.
Think of it like this. Inside the instrument case, which is airtight, there's this very sensitive, flexible diaphragm.
Okay, like a little metal balloon or something.
Sort of, yeah. Made of metal, usually. And the whole game is creating a temporary difference in pressure between the inside of this diaphragm and the outside of it, which is just the air inside the instrument case itself.
And it does that by letting the air get to those two places at different speeds.
Precisely. So the inside of the diaphragm, that gets air straight from the static line, unrestricted. Whatever the atmospheric pressure is right now, bam, it's inside the diaphragm. Instant update.
Instant update inside. Now, the space outside the diaphragm, so just inside the instrument case itself, that air also comes from the static line. But, and this is the absolute key, it has to go through a tiny restricted opening. A bottleneck?
Ah, the famous calibrated leak. I've heard that term.
That's the one. That little calibrated leak is the entire magic trick of the VSI. It controls how quickly the pressure inside the case can change.
So when you're just sitting on the ground or flying perfectly level for a while.
Right. Everything has time to settle. The air slowly seeps through that calibrated leak, and the pressure inside the diaphragm and the pressure in the case become equal. They equalize.
Equilibrium.
Exactly. And when the pressures are equal, there's no force on the diaphragm, and the linkage attached to it makes the needle point to 0. Happy days.
But the moment we climb or descend, that balance is gone. Let's say we pitch up, start climbing.
Okay, climb. As the aircraft goes up, the outside air pressure, the static pressure, drops.
Yeah.
Instantly. And because the inside of the diaphragm has that direct line, the pressure inside it drops instantly, too.
Okay.
But the pressure in the case around the diaphragm, it can't drop that fast. It's stuck behind that calibrated leak. The air has to slowly leak out of the case through the restriction.
Ah, so for a moment, the case pressure is higher than the pressure inside the diaphragm.
Exactly. And that pressure difference pushes on the diaphragm, makes it contract or maybe expand, depending on climb or descent. Anyway, it moves.
And that movement pulls on the needle linkage.
Pulls the linkage, moves the needle up, showing a climb. And it keeps moving until the pressure difference stabilizes at a certain ratio. That ratio is, calibrated at the factory to match a specific rate. 500 FPM, 1,000 FPM, whatever you've set up.
And once you hold a steady climb, the leak rate sort of matches the rate of altitude change, and the needle holds steady.
That's the idea. The differential becomes constant for a constant rate of climb or descent.
Okay, that makes sense. The leak is the key. So we've got the mechanics. Now let's talk about what the pilot actually sees, because this causes confusion, especially for students. Trend versus rate.
Oh, absolutely critical. This distinction is huge for actually using the instrument effectively. So trend information, that's the first thing you see.
The immediate twitch of the needle.
Exactly. The direction the needle starts moving. You pull back, pitch up, the needle immediately flicks upwards. It's just saying, hey, something's changing vertically. That's the trend.
But you can't, immediately trust that flick to tell you you're climbing at, say, 500 feet per minute.
No, absolutely not. That initial movement is just the trend. The actual rate information comes later. That's the stabilized reading, when it settles on 500 FPM or 700 FPM or whatever steady rate you've established.
And the gap between seeing that first twitch, the trend, and getting the reliable rate.
Yeah.
That's the infamous lag.
That's the lag. It's the time it takes from when you start the climb or descent to when the VSI actually shows the correct stable rate. And for a standard VSI, the kind in most trainers, it's surprisingly long.
How long are we talking?
Typically 6 to 9 seconds.
6 to 9 seconds. Wow. Okay, think about that. You make a control input, and you don't get accurate feedback on the result for almost 10 seconds.
It feels like an eternity when you're trying to fly precisely.
Yeah, it's like driving a car where the speedometer only updates every, block or two. You're flying based on old news.
It's a great analogy, and that lag exists purely because of the mechanics we just talked about. It takes those 6 to 9 seconds for the pressure inside the case, slowly bleeding through that calibrated leak, to establish that new, stable pressure difference relative to the diaphragm.
Which is exactly why instructors always say, don't chase the needle.
Right, absolutely. If you keep reacting to what the needle said, 8 seconds ago, you'll just start pitching up and down, creates oscillations.
Pilot-induced oscillations. The classic error. And I guess rough air turbulence just makes it worse.
Oh, much worse. Turbulence makes the static pressure fluctuate anyway, and if you're making jerky control inputs on top of that, the VSI can become almost useless, just bouncing around erratically. The lag gets extended, the readings are unstable.
Okay, so if this lag is just built into the basic design, how do fancier planes deal with it? There must be a better way now.
There is. The engineers knew this was a limitation. Which leads us to the more modern solution you sometimes see.
The instantaneous VSI, the IVSI.
Oh, that's the one. The instantaneous vertical speed indicator. It basically finds a way to, cheat that calibrated leak lag.
How does it do that? Does it still use the pressure difference?
It does, yeah. It still has the diaphragm and the case and the pressure differential, but it adds another layer of technology inside, accelerometers, little sensors that detect vertical acceleration.
Okay. So it feels the start of the movement.
Exactly. A normal VSI only knows you're climbing after the pressure difference builds up. The IVSI uses those accelerometers to detect the instant you start accelerating upwards or downwards. It senses the very beginning of the pitch change.
And uses that acceleration data too.
To drive the needle immediately. It essentially predicts what the final rate will be based on that initial acceleration, and it electronically compensates for the pressure lag from the leak.
So it gets rid of most of that 6 to 9 second delay.
Pretty much, yeah. It gives you a much more immediate, almost predictive vertical rate reading. It's a huge improvement for precise instrument flying.
But for those of us flying with the standard classic VSI, we just have to live with the lag. Discipline is key.
Absolutely. You make your pitch change using the attitude indicator, set your power, and then you have to wait patiently. Let the VSI settle down and tell you the result. Don't react instantly to the needle.
Patience and discipline. Got it. Okay, let's switch gears to practical stuff. Pre-flight. We have to check this thing before we even start the engine, really. What are the checks?
Right, standard procedure. The sources point out 2 main checks. First, just sitting there on the ramp before you even taxi, check the VSI. It should read pretty close to 0.
Okay.
Second, check it again right before you line up for takeoff. Just confirming it's still indicating level 0 pressure differential.
Now, what if it's not perfectly 0? Sometimes you see it sitting just slightly below, maybe indicating like minus 50 FPM descent while you're parked. That can worry a student?
Yeah, that's super common. A little bit of wind over the static port, maybe temperature changes. It can be slightly off. The rule of thumb is if it's just slightly off, say, within maybe 1 or 2 needle widths, perhaps up to 100 FPM. Either way, just make a mental note of that reading.
So if it reads minus 50 on the ground,
then minus 50 becomes your new 0 reference for the flight. When you want level flight, you aim for minus 50 on the VSI. No big deal.
But if it's way off, like showing a 300 FPM climb while parked,
then something's definitely not right. That's significant. Could be an instrument issue, maybe a partial blockage somewhere. That needs maintenance attention before flight. Don't fly with it like that.
Good to know that tolerance. Okay, so we're happy with the 0 reference. We line up, power up, take off, roll. Lift off. What should we see then?
Well, that's the first big confirmation. As soon as you lift off, that needle needs to show a definite trend upwards, a positive indication. That confirms you are actually climbing, leaving the ground.
Your first positive confirmation of being airborne, really.
Exactly. And then, once you establish your climb attitude, set your power for the climb. Again, you wait. Let the needle stabilize.
Let the lag catch up.
Let the lag catch up, and then you see what your actual rate of climb is. Maybe 700 ppm, maybe 800 ppm.
And this really highlights something important. If we're aiming for, say, a 700 ppm climb, we don't use the VSI to set that initial pitch, do we?
Absolutely not. That's probably the biggest operational mistake you can make. The VSI is a rate confirmation instrument. It confirms the performance you get from your pitch and power settings.
So you use the attitude indicator for pitch.
Right. Set your desired pitch attitude on the AI. Set your climb power on the throttle or engine instruments. Hold that steady. Then, after the lag, you look at the VSI to see what rate of climb resulted.
And if it's not quite 700 FPM, you make a small pitch or power adjustment and wait again.
Exactly. Small adjustments, wait for it to stabilize. Trying to fly the VSI needle directly just leads to chasing it all over the sky. Pitch and power first, then VSI confirms the rate.
It's amazing, really. Such a fundamental instrument, but its proper use relies entirely on understanding its built-in delay, that calibrated leak, that lag.
It really does. So yeah, next time you're looking at that VSI needle moving, remember the little dance happening inside, that differential pressure built up slowly because of the calibrated leak.
Slowing down the case pressure.
Right. And always factor in that 6 to 9 second lag. Fly your attitude indicator first, let the VSI tell you the result later.
Essential stuff for flying smoothly and accurately. Okay, to wrap this up, let's leave our listeners with something to think about. Connecting the VSI back to the whole pitot-static system.
Sounds good.
Since the VSI relies completely on that static port feeding it pressure and on that calibrated leak, letting pressure change slowly inside the case, what would happen if the static port suddenly got blocked? Say, iced over in flight.
Ooh, good question. Think about the air trapped inside the system.
Yeah. What pressure gets trapped inside the VSI case? And what happens to the pressure inside the diaphragm if you then try to climb or descend with that blocked port? How would the VSI behave? Would it read 0? Would it read incorrectly?
That trapped pressure is the key. What happens to the differential then? Something definitely worth puzzling out.
Absolutely. Food for thought. Well, thank you for joining us for this deep dive into the vertical speed indicator. Fly safely out there.
Fly safe.
And we'll catch you on the next deep dive.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.